Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In this video, we will be taking up a concept called haloalkanes, which is a part of organic chemistry. So from its name, if you say haloalkanes, so you can predict the structure, right? If I say alkanes, then they are the compounds having a general formula CnH2n plus 2. Right. So if I say haloalkane, what does that mean? From alkane, I will remove a proton H plus. Sorry, I'll remove a hydrogen group. I will convert it into a alkyl group, and in that alkyl group, I will substitute a halo or a halogen group. Right. A halogen I will substitute. Let me represent the halogen as X. Then it will give me CnH2n plus 1 X. So here I come down to the general formula of haloalkane, which is CnH2n plus 1 X. So if in an alkane I replace a hydrogen atom with any halogen, I get my class of compounds commonly known as haloalkanes. So let's see. The compounds derived from alkanes by the replacement of one or more hydrogen atoms by their corresponding number of halogen atoms. Okay, whichever number of hydrogens I'll be removing, I'll substitute it or I'll compensate it with that much number of halogen atoms, and I get my class of alkyl halides or haloalkanes. Okay, they are commonly known as alkyl halides too. So haloalkanes by the replacement of one or more hydrogen atom by corresponding number of halogen atoms, which may be fluorine, chlorine, bromine, iodine, anything, and they are termed as haloalkanes. Alkyl halides or haloalkanes, will be using them synonymously, and alkyl halides are represented by the general formula CnH2n plus 1 X, where X is any halogen atom. Now, if I see the orbital structure of this, in alkyl halides, the carbon halogen sigma bond is formed by the overlapping of sp3 hybrid orbitals of carbon and half-filled vacant orbital of halogen atoms, right? So, in case if I am taking up only one halogen substituted carbon, let me see, here the carbon is, or it is representing the formula of CH3Cl. So, in this what happens? The p orbitals, carbon is involving its sp3 hybridized orbitals to overlap with s orbitals of 3 hydrogen atom, and here what it is doing, one of the sp3 hybridized orbital is overlapping with a vacant or singly filled orbital of chlorine. Okay, a singly filled p orbital of chlorine. If I see chlorine, then its atomic number is 17, and if I say its, or if I write its electronic configuration, I get a formula 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so 3p is supposed to be 6. In order to fulfill that, or in order to form a bond with carbon, it is utilizing its p orbital here, 3p, which is the outermost orbital, to overlap with the sp3 hybridized orbital of carbon, resulting in the formation of carbon chlorine sigma bond, as it is formed by the head-on overlapping of sp3 hybridized orbital with that of singly filled or half-filled p orbitals of chlorine. Now, if I see haloalkanes, how they are classified, first of all, depending upon the number of halo groups. Okay, so first is monohalogen, dihalogen derivative, and polyhalogen derivatives also. So, if one hydrogen attached or one halogen atom is attached to the carbon atom, then it falls under the category of monohalogen, because as you can see from the name, mono means one. So, if in the case of the haloalkane, only one halogen atom is substituted, they fall under this category. Now, if I see dihalogen, obviously it means two halogen atoms are substituted. So, here what happens, if I see the example CH2Cl2. So, what I find here is, from my alkane CH4 methane, I have removed two hydrogen atoms, and to that two hydrogen, or in place of two hydrogen atoms, I have added two chlorine atoms. Okay, then I get CH2Cl2. This becomes my dihalogen derivative. And if beyond that, I can break any number of carbon bonds or carbon hydrogen bonds and I will replace it with halogen, I will get my polyhalogen compound or derivative. Now, these are the these are derived by the replacement of two hydrogen atoms by two halogen atoms, and dihalogen derivatives are again of the following types. So, if I say dihalogen derivative, if it is single carbon, then I don't have any issue. I can remove all the four hydrogens, I can substitute them with halogen atoms. But if there are two or more carbon atoms, let's say I am giving you ethane. Okay. Now here also I can make my monohalogen, dihalogen, polyhalogen derivatives. So monohalogen is okay, fine. I'll replace any of these three hydrogen atoms on the two carbon atoms. Let me say carbon 1, 2. But if I say make it dihalogen, now what are the possibilities? You can either break one hydrogen bond from here and one hydrogen bond from here to give you CC, Cl, Cl and CH2, CH2 are present as it is. Okay, this is one possibility, and the second possibility is I will remove both the hydrogen atom from the same carbon atom, right? This also I can do. I can write it like this. Now, this gives me two different class of dihalogen derivatives. First is the geminal dihalides, which I call the gem dihalides. It means, see, somewhat gem sounds familiar to same, right? So gem means both the halogen atoms are attached to one particular carbon atom only. Okay, so if I'm deriving it this way, that both the hydrogen atoms are removed from a single carbon, and in place of those hydrogen atoms, those two hydrogen atoms, two chlorine atoms are substituted, then it gives me a class of geminal dihalides. And but if two hydrogen atoms are removed from separate carbon atoms, and to compensate that, two chloride bonds are formed between the separate carbon atoms, then they fall under the category of vicinal dihalides. Okay, we write them as VIC, vicinal dihalides. As you can see here, the example ethylene chloride. I'm sorry, there's a printing mistake. It's ethylene chloride. Ethylene chloride, here what happens? Both the chlorine atoms are attached to the same carbon atom, right? So here it also falls under the category of geminal dihalides. Now if I see the second one, vicinal dihalide, here the chlorine atoms are attached to two different carbon atoms. Got it? Now second is alpha gamma, which is terminal dihalides. That means if there are three carbon atoms, let's say, this is the structure of propene, right? So here what happens, if there are two carbon atoms where from the end or the terminal carbon atoms the hydrogens are removed and to them the chlorine atoms are attached, then they fall under the category of terminal dihalides. Means terminal means end. Okay, so if the end carbon and the end carbon hydrogen bonds are replaced with chlorine, they fall under the category of terminal halides. Okay, this is called gamma, alpha, omega halides. Now if I see trihalogen derivatives are derived by replacing three hydrogen atoms similarly. So general formula is CnH2n-1x. This is an example where I was having CH3 and CH3. I'm sorry, here also there is a mistake. So let me write the structure. It is CH3, CH2, CH3. Now to this, what I am doing here, I am replacing these three hydrogen atoms with three chlorine atoms. There I am getting a trihalide. Okay, so these are pretty simple structures where you can derive or you can assume what the compound will look like simply from the name of the compound. Now if I classify monohalogen derivatives in further terms, right? First of all, if I try to mention the degree of carbon atoms, right? So alkyl halides are classified as primary, secondary and tertiary depending upon the nature of carbon halogen bond. Okay, if I am saying the carbon halogen bond is formed between a carbon which is attached to a single carbon only, then this falls under the category of 1 degree halide. If the carbon is attached to 2 carbon atoms or 2 other carbon atoms, and which carbon? The one that is forming the bond with halogen. Okay. So if that carbon is associated to 1 carbon, it is falling under the category of primary halide. If it is associated to 2 carbon atoms, it is falling under the category of secondary halide. And if it is attached to 3 carbon atom, then it is falling under the category of tertiary halide. And of course, if it is forming with one bond with 1 carbon, all the rest 2 bonds will be satisfied by hydrogen. So similarly, if it increase the degree of carbon, the number of hydrogen atoms will gradually decrease. Okay. So here are certain examples of primary alkyl halides. See here, the carbon atom is attached to only one alkyl group. This R group stands for alkyl group, right? In case of secondary, what is happening? The carbon atom is attached to 2 carbon atoms, 2 other carbon atoms. Now in case of tertiary, it is attached to 3 other carbon atoms. I'm sorry, here there is a halogen group. In place of H, there will be X, any halogen groups. Okay. Now if I say compound containing sp3 carbon, now what do you mean by sp3 carbon? That means all the carbon, hydrogen, carbon, halogen or carbon, carbon, they form single bonds, then only they will fall under the category of sp3 hybridized carbon atom. So in case of alkyl halide, simple alkyl halide, if I say 1 chloropropane, obviously what is happening here? CH3, CH2, CH2, Cl. So all the bond between carbon, 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 hydrogen and carbon chlorine, all are singly bonded with each other. Hence they fall under the category where the carbon halogen bond is sp3 hybridized. Now if I see allylic carbon, now what do you mean by allylic carbon? See, if the carbon hydrogen or the carbon halogen bond is associated to a carbon which forms again double bond here, this kind of system is called as a allylic system. That means the double bond is interpreted by a single bond, or the double bond is interfered by a single bond. Okay, then it falls under the category of allylic carbon. Halogen atom attached to allylic carbon, that is the carbon atom which is next to the carbon-carbon double bond. Okay, this is called as a allylic system. You can see here, this carbon halogen bond is interrupted by a single bond before entering or before encountering a double bond. Okay, so this forms an allylic system. Now if I say the carbon containing sp2CX bond, okay, sp2 means to which or particularly this carbon atom which is attached to the halogen atom, that is attached to a sp2 hybridized or directly attached to a sp2 hybridized carbon. So if I say this, chlorine is attached to a carbon which is forming a double bond. So this carbon is basically a sp2 hybridized carbon. Therefore, they come under the category of vinylic halides. Okay. Next is compounds containing sp. That means this carbon atom is triply bonded. Okay. So here dihalides, the halogen atom is attached to one of the carbon atoms of the C triple bond C. Okay, bromoethine. Now let us see some isomers of monohalogen compound. Now what do you mean by isomers? If I see the name, iso somehow means same. So such class of compound which have same molecular formula but different structural formula, they fall under the category of isomers. Same molecular formula but different structural formula. They fall under the category of isomers. Now if I say chain isomerism, this is due to different arrangement of carbon in alkyl group. Let's say if I'm taking this example, then here what is happening? All the 3 or 4 carbon atoms are joined in a straight line fashion, and they are given the name 1-chlorobutane. Okay. In this case, what happens? The butane or the 4 carbon atoms are end to end connected in a straight line fashion, and they give you 1-chlorobutane. Now, if I see the second one, I can arrange it this way also. I can do a branching at second carbon, 1-chloro-2-methyl propane. So, generally what happens, these two structures, they have the same molecular formula if I see, but the structural formula or the arrangement is different. Second is position isomerism, which is due to, this is due to the different position of halogen atom in the molecule. Let's say here, the halogen atom is attached to carbon number 1. But if I see the second example, here the halogen atom is attached to carbon number 2. But will it be possible to attach this chlorine here? Obviously no, because if the chloride ion goes to this place or the chlorine atom goes to this place, then I'll start counting from here. So this will become ultimately my second position only. Okay, that would not make any difference. So here I get 2 isomer. One is the first carbon substituent and the second is the second carbon substituent. Now here there is a optical isomerism. What is optical isomerism? Optical isomerism is basically due to the presence of an asymmetric carbon. What do you mean by asymmetric carbon? Means a carbon which is attached to 4 different groups. Okay, we call it a chiral carbon. It is called chiral carbon. That is the carbon which is attached to 4 different groups or 4 other groups. If I see here, the carbon is attached to CH3, C2H5, hydrogen and chlorine. So all the 4 groups are different. That's why this is a chiral carbon, and chiral carbon is represented by a carbon star. Okay, the star denotes the presence of an asymmetric carbon. So here what happens? This falls under the category of optical isomerism. Now, conformational isomerism. Conformations means different arrangement due to the rotation of carbon-carbon sigma bond. So, if I can rotate the carbon-carbon sigma bond in different directions, then the possible isomers which I get is will be falling under the category of conformational isomerism. Okay. So, this was some general idea about alkyl halides. Now we will move on to the general methods of preparation of alkyl halides. The first one is from alcohols. Okay. So what happens? First is acid catalyzed hydration. So hydrogen halides can be prepared. Hydrogen halides can be prepared when the ROH or alcohol in the presence of H plus gets reacted with another halogen ion. Okay. Suppose one alcohol is reacting with another alkyl halide, then the halogen part of that particular alkyl halide will substitute the OH minus in this to give you alkyl halide. So if I say ROH, it's having lone pair. So in presence of H plus on an acidic medium, it will give you ROH2 plus. Now what will happen? This water will get liberated out to give you a carbocation. Now when this carbocation reacts with some other alkyl halides, let's say Rx or any X minus from any source, then that X minus substitutes or gets combined with this R plus to give you a group of alkyl halides. Since the nucleophilicity, that is a tendency to donate electrons to the carbon atom of the halide ion decreases in the order I minus, Br minus, Cl minus. Why? Because as we move from iodine to chlorine, the electronegativity increases as the size decreases. So, because of that increasing electronegativity, the negative or the I minus charge donation effect decreases in this order. I minus greater than Br minus greater than Cl minus. So, the order of reactivity becomes Hi greater than Hbr greater than HCl. Now, different alcohols, the reactivity is, see, here there is generation of carbocation. So, if the carbocation or there are certain factors which stabilizes the carbocation, then they will obviously enhance this reaction. So, the order is allylic carbon greater than 3 degree, greater than 2 degree, greater than 1 degree. Okay. Another method is I can react ROH with HCl, concentrated HCl and anhydrous ZnCl2. It is important to note here is This reagent, concentrated HCl plus anhydrous ZnCl2, has a specific name or a special name given to it. It's called Lucas reagent. Okay, Lucas reagent. It is a distinguishing test of the order of different alcohols. Basically, tertiary alcohols react very rampantly with Lucas reagent, and the order or the reactivity gradually decreases as we move from tertiary to primary. HCl do not require ZnCl2 for 3-degree alcohol because 3 degree is very reactive. Okay. This mixture of 1:1 concentrated HCl and anhydrous ZnCl2 is called Lucas reagent and is used to distinguish between 3-degree, 1-degree, 2-degree and 1-degree alcohol because their reactivity towards this reagent is 3-degree alcohol greater than 2-degree greater than 1-degree. Okay. So here if I see what is the mechanism, I have already said you the result formation of carbocation, and if you see there are any other factors which leads to stability of carbocation like hydride shift or methyl shift. So first we have to go for that. We have to stabilize our carbocation, then we will go for nucleophilic attack. Okay. And the second is from phosphorus halide. These are some direct reactions you have to remember. If you are reacting alcohol with PCl5, you get RCl plus POCl3 plus HCl. If you are reacting with PCl3, so as you are decreasing the number of halogen atoms, here the product is also, normally what happens, if you have 5 chlorine atoms, then you go for PCl3 and HCl. But if you have three halogen atoms, then you can write result or the formation of H3PO3. Okay. So if I'm saying PCl3, I'll get RCl plus H3PO3. If I'm writing PBr3, then I'll also get RBr plus H3PO3. And if I'm reacting PI3, I'll get Ri and H3PO3. Fourth method gives very good yield of 1-degree haloalkane, but poor yield of 3-degree and 2-degree. This one. Okay, this gives very good yield of 1-degree, but poor yield of 2-degree and 3-degree because secondary and tertiary alcohol on heating forms alkene. PBr3 and PI3 are obtained in situ by the reaction of red phosphorus and bromine or iodine. Like I can write red phosphorus plus Br2 or red phosphorus I2. Okay, these are also highly reactive with that. And third method is action of thionyl chloride, and actually this method for the preparation because the other two byproducts, that is SO2 and HCl, these are gaseous and they can easily escape out the reaction medium, leaving behind my alkyl halide free. Okay, so I did not use to implement any other techniques to separate RCl from SO2 or HCl. So if I see ROH reacts with SO2 in the presence of, or SOCl2, thionyl chloride, in presence of pyridine, it gives you RCl along with SO2 and HCl. This method is the preferred method because other two byproducts are escapable gases. SOBr2 is less stable and SOI2 does not exist. Thus, RBr and Ri can't be prepared by Darzon's method. Yeah, this has a name also and it's called as Darzon's method. Okay, and the next reaction is Hunts-Ticker reaction. What happens here? RCO, silver salt of carboxylic acid, basically reacts with carbon tetrafluoride reflux and Br2 to give you RBr plus CO2 plus HBr. This is a direct reaction you have to remember. So CH2COAg plus Br2 gives rise to CH3CH2Br plus CO2 plus HBr. The reaction gives product with one carbon atom less than the fatty acid. Okay, carboxylic acid also called as fatty acids because the C double bond O and O group is getting removed as CO2. So the resulting carbon will, or the resulting product will have a one carbon atom less than the parent product. And the yield of halide is 1 degree, 2 degree, 1 degree greater than 2 degree, greater than 3 degree. The next method is halide exchange method. Here you have two reactions, namely Finkelstein reaction and Schwartz reaction. So in Finkelstein reaction, what happens? This is an ideal method for preparation of alkyl iodide. Here what happens, any Rx you are taking, you are reacting it with NaI in the presence of dry acetone. It directly gives you Ri, alkyl iodide, plus NaX. Now NaCl or NaBr is precipitated in dry acetone. It facilitates forwards reaction. Now Schwartz reaction, it is basically for the preparation of fluorides. So Finkelstein was used for the preparation of iodides, and Schwartz reaction is used for the preparation of fluorides basically. So here also what happens, if I am reacting any alkyl halide with AgF, then again halogen exchange takes place to give you alkyl fluoride plus AgBr. Other than AgF, Hg2F2, COF2 and SbF3 can also be used. Next method is halogenation of alkane, and this is a chain reaction. This is a free radical mechanism. So here what happens, RH in the presence of X2 and UV light. So wherever you are seeing UV light, you will go for this method, or like chlorination. Basically it is used for chlorination, and you will use your free radical mechanism. It is a chain reaction where there are 3 steps. One is chain initiation, one chain elongation, and the one is chain termination. Okay, chain elongation or chain propagation, and one is chain termination. So in iodination, being reversible process, requires the presence of oxidizing agents such as HiO3 and concentrated HNO3. Abstraction of hydrogen for a particular halogen follows the order this. Okay, this is the order of reactivity for this reaction, and the order of reactivity of like halogen is F2, Cl2, Br2 and I2. And basically what happens, the reaction with fluorine is so fast that we usually don't carry it out, and with that of iodine is very slow. So ideal method is for preparation of Cl2 and Br2. And the next method is direct halogenation, again this chain reaction only. Fourth is addition of hydrogen halide to alkene. So if I am seeing hydrogen halide, if I am adding this HX, then it can break the pi bond, this H and X, it will break off as H plus and X minus. Now this double bond will attack the H plus one, then to that the other carbon will have a positive charge, then to that positive charge the X minus will come and get attached. But here if it is a symmetrical alkene, then this can occur. Okay, whichever side you can add H and X, doesn't matter. But if there is an unsymmetrical alkene like this, CH3, CH2, CH, then you have 2 possibilities, right? If I am adding HX in both the cases, then you have 2 possibilities. One is CH, X and CH3. The next possibility is CH3, CH2, CH2, X. So here what happens, first thing is, in one case the negative ion is going to the second carbon, in the other case the negative ion is going to the first carbon. So there is a confusion, there is a battle between which one will be the major product and minor product. So in this case we follow a rule called as Markovnikov's rule, and according to Markovnikov's rule, whenever we have an unsymmetrical alkene, the negative part always goes to that carbon atom which is having lesser number of hydrogen atoms. So if I see both this carbon is having a single hydrogen atom only, and this carbon is associated with 2 hydrogen atoms. So as per Markovnikov's rule, I will be taking up this carbon to be the site of attack of the negative ion X minus. Okay. Hence this falls out to be my major product. Okay, so reaction follows electrophilic addition mechanism. Why electrophilic addition? Because in the first step H plus was getting added. So in the presence of in the absence of a special reagent called as H2O2 or peroxide, in the absence of this, Markovnikov's rule will be followed. But if there is the presence of H2O2 or peroxide, then anti-Markovnikov's addition happens. And anti-Markovnikov's addition, as per the name, is just the opposite of Markovnikov's. Here what will happen, the negative side will go to that carbon atom which is having more number of H2, okay, more number of hydrogen. HCl and HI do not show the peroxide effect, and it is basically shown for Br, RBr. Product may be obtained due to 1,2 hydride or 1,2 methyl shift as per the stability of carbocation. Addition of bromine in CCl4 to an alkene results in the discharge of reddish brown color, and this is the bromine water test. Constitutes the discharge of bromine constituent, an important method for detection of double bond in a molecule. So what happens if I am adding an alkene to bromine in the presence of water, the brownish color of bromine is getting discharged or it is getting colorless. Okay. So if this colorless happens, this shows the presence of unsaturation, and this is basically termed as the bromine water test. So if you have to suggest any test for distinguishing between the test between to test the presence of unsaturation, then bromine water test is an ideal test for that. So this was all about the preparation of alkyl halides. In the next video, we will be taking up the physical and chemical properties of alkyl halides. I hope you are clear with this till now. So let's all meet in the next lecture. Thank you so much for watching.